Okay, let us start with an introduction to the numerical solution of systems of linear equations of the form AX equal B. As a motivation, consider this truss structure that is simply supported and subject to this uniform load in this upper flange. This is the stiffness matrix K of this structure, and command SPY in MATLAB reveals its sparsity pattern. We can see that only a few non-zero entries concentrate along the main diagonal. The matrix is very sparse, the reason being that each node is connected only to itself and to its neighboring nodes, but not to the rest of the nodes in this structure. Okay? By solving the linear system KU equal F, we can obtain the deformed structure and axial stresses. If we go to a three-dimensional structure with either 10 or 20 spans in each direction, we again see very sparse matrices with only a small fraction of entries that are non-zero. We are already familiar with finite element matrices. We've discussed mass matrices, that is, integrals of products of shape functions, and also diffusion matrices, that is, integrals of products of gradients of shape functions. These matrices are typically large for fine meshes and also very sparse due to the compact support of shape functions and the connectivity between nodes. Very often, and that's the case of mass and diffusion matrices, they are also symmetric and positive definite. Okay? So we'll be interested in numerical techniques that exploit all these properties of finite element matrices: large size, sparsity, symmetry, and positive definiteness. We'll be interested in the solution of large systems of equations involving thousands, tens of thousands, hundreds of thousands, and even millions of equations and unknowns. And because of this, our main goal is to develop numerical strategies for the efficient solution of these large systems of equations. Okay? The keyword here is efficiency. Before doing that, let us briefly review the classical algebraic point of view regarding the existence and uniqueness of solution of a linear system AX equal B. And let us please recall that the following statements are equivalent. Statement 1, the system AX equal B may be solved for any right-hand side vector B. Statement 2, if the system has a solution, then the solution is unique. Statement 3, the homogeneous system with zero right-hand side vector has zero solution. Statement 4, all the columns, or also all the rows in matrix A are linearly independent. Statement 5, there is a square matrix called inverse matrix, such that the product of A times A inverse or A inverse times A equals the identity matrix. Statement 6, matrix A has a non-zero determinant. Okay. This review highlights two very important notions in the classical algebraic point of view, those of inverse matrix and determinant. Okay, a very important message is that from a numerical point of view, these existence and uniqueness conditions are of little relevance, and the notion of determinant and inverse matrix, they play a rather minor role. Okay? Regarding determinant, computing a determinant is very expensive. It involves a lot of operations, and out of that, it is difficult to decide whether it is zero or not. Note, for instance, that the determinant of a matrix A multiplied by a scalar gamma equals gamma to the power of n being the problem dimension, determinant of A, which means that if A is, say, 0.1 and n is large, gamma to the power of n may be a very, very small number. Okay. Regarding the computation of the inverse matrix, again, it may be computationally expensive. Okay. Note also that computing an inverse matrix may be understood as solving n systems of linear equations. Let us discuss this idea more closely in this blank page. So, a classical viewpoint would suggest the following. When faced with linear system AX equal B, we could think of the following algorithm. First, compute determinant of A. Second, if determinant of A is different from 0, then compute matrix C as the inverse of A. Third, compute the solution X start of the system as the product of C times B. Okay. Well, this is an inefficient way of solving the problem. To illustrate this, two arguments. Okay. First, we would not even use this idea for n equal 1. Indeed, for solving AX equal B, we would first check if A is different from 0, and then compute the solution X as B over B. So that's one division. We would not compute C as 1 over A and then X as C times B. This would be one division and one product. So this second approach is twice as much the number of operations as this. Okay. Another argument to illustrate that the explicit computation of an inverse matrix is inefficient is the following. Matrix A inverse may be thought as composed of its columns. So first column is x1, second column is x2, third column is xn. Okay. Let us also think of the identity matrix I as composed of its first column, second column, third column, and so on. So, obtaining A inverse such that A times A inverse equals the identity, this is equivalent as solving these n linear systems, AXI equal EI, for I from 1 to n. So the initial job was solve one linear system AX equal B, Okay, and let us stress this one. And if we want to use the inverse matrix, we are suggesting to start by solving n systems with a very large value of n. This is clearly not an efficient way to proceed. Things can be much worse, and in fact, classical methods such as grammar method, this very elegant technique based on computing determinants, simply cannot be used for large systems. The reason being that the number of operations, the total operation count TC, involves n factorial, which grows brutally even for modest values of n. Okay? For a very modest system size of 100, Grammar's methods require 10 to the power of 158 operations, which means an incredible amount of time even for a supercomputer. Okay? So, from a numerical practical point of view, the keyword will be efficiency. And efficiency, we mean both the number of operations, CPU time, and the memory storage requirements. And we will also pay attention to the applicability of each numerical technique depending on the properties of matrix A. In this unit, we'll discuss basically three types of strategies. On the one hand, systems with a trivial solution will be solved by means of simple algorithms. By trivial, we mean systems with either a diagonal or a triangular matrix. Then we will discuss direct methods. These methods are based on transforming the original system AX equal B into an equivalent system with trivial solution. These methods provide the exact solution, except for rounding errors, after a finite number of steps. Okay? We will finally discuss iterative methods. That is, methods where we start with an initial guess of the solution and then compute a sequence of approximations. So starting from x0, we compute x1, x2, x3, a sequence of solutions that will hopefully converge to the solution x star of the linear system.